Hey, have you ever said something like, oh, that has a weight of 10 kilograms? I bet you have. We all do it. But, in the world of physics, that's actually a classic mix-up. So today, we're going to clear up that confusion once and for all. Let's find out what the real difference is between mass and weight.
All right, so let's dive right into this whole everyday confusion. It really all starts with a super simple question, one you might hear at the grocery store, or maybe even one you've asked yourself.
So, let's just tackle this head-on. Is it actually correct to say an object has a weight of 10 kilograms? I mean, you've probably said it, I know I have, but scientifically, the answer is a big, firm no. And figuring out why, well, that's the key to this whole thing.
See, we throw these words around, mass and weight, like they're the same thing, but they are totally different concepts. And getting this right is super important, so let's start with the first one, mass.
Okay, first up, mass. Let's really get a grip on what this is. For a second, just forget everything else and think about the actual stuff that makes up an object.
At its core, it's a pretty simple idea. Mass is literally just the amount of matter, the physical stuff an object has. Think of it as all the atoms and molecules just packed inside something.
So mass has a few really key properties. First off, it's a measure of inertia. That's an object's resistance to being pushed around. We measure mass in kilograms or kilograms. But listen up, because this is the most important part. An object's mass is always constant. It never ever changes, no matter where you go. Your mass is the exact same on Earth as it is on the moon or even floating out in deep space. And last but not least, if an object exists, it has to have mass. It can't be zero.
Okay, so if mass is the stuff, then where does weight fit in? Well, this is where a very familiar force makes its grand entrance. I'm talking about gravity. So here's the big difference. Unlike mass, weight isn't something an object just has. It's not part of its identity. Instead, weight is a force. To be specific, it's the measurement of how hard gravity is pulling down on all that stuff, on all that mass. And there's this simple but really powerful formula that connects the two. You'll see it written as P equals m times g. Now, P here stands for weight. Fun fact, that comes from the Latin word pondus, but you might also just see it as a W. Then m is the mass we just talked about, and g is the acceleration due to gravity.
Let's break that down a bit more. Weight, or P, is a force, right? So its official unit is the Newton. Yep, named after Sir Isaac Newton. Mass, our m, is that constant we talked about, and we measure it in kilograms. And g is simply the strength of the local gravitational pull. Here on Earth, that pull is about 9.8 meters per second squared.
All right, theory is all well and good, but this next part is where it's all going to click into place. Let's put these ideas to the test with a little thought experiment. We're going to take a trip from Earth all the way to the moon.
This table just lays it all out perfectly. So imagine we have something with a mass of exactly 1 kilogram. Here on Earth, its mass is, well, it's 1 kilogram. Simple. Its weight, though, is about 9.8 newtons. Now, you might sometimes see this written as 1 kilogram force, or kgf. That's just a way of talking about weight that feels a little more familiar. Okay, now let's blast off and take that exact same object to the moon. What's its mass? It's still 1 kilogram. The amount of stuff didn't change at all. But its weight? Whoa. It plummets all the way down to just 1.6 newtons.
So why that huge drop in weight? It's pretty simple, actually. The moon's gravity is only about 1/6 as strong as Earth's, so the force pulling on that 1 kilogram of matter is just way, way weaker.
And that really brings us to the most crucial point of all. An object's mass is this solid, constant number that never changes. Its weight, on the other hand, is totally dependent on where it is and how strong the gravity is in that spot.
So at this point, you might be thinking, okay, that's a pretty cool piece of physics trivia, but why does this actually matter in the real world?
Okay, let's put it all side by side one last time just to lock it in. Think of it like this. Mass is the essence of an object. It's the matter itself. It's constant, and we measure it in kilograms. Weight, though, is the effect of gravity on that mass. It's a force, it changes depending on your location, and we measure it in newtons.
And this is where it becomes absolutely critical. For, say, an engineer designing a bridge or a scientist planning a rocket launch, this is not just a fun fact. I mean, if you try to calculate the forces on a spacecraft using its mass instead of its weight, well, your calculations are going to be disastrously wrong. You have to know the force a structure can handle, and that's its weight, not just the amount of stuff it's made of.
And that brings us right back to the beginning. The next time you step on a bathroom scale, just take a second and think. Are you measuring your mass, or are you measuring the force of Earth's gravity pulling down on you? I mean, the scale spits out a number in kilograms or pounds, but what it's really measuring is weight. And now you know exactly why.